Hello everybody and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going on to our second lesson in DNA, which is all about Chargaff's rule. And so let's jump right into it. So again, we talked about AT, C, and G in the last lesson. Scientists really weren't sure about how much AT, C, and G different organisms had. And so a lot of scientists just thought, oh, well, they're probably equal. You probably have 25% A, 25% T, 25% C, and 25% G. But Erwin Chargaff in the 1950s decided to test this. So this is Erwin Chargaff, a signed headshot for some reason. And this is what he found. So you've got, in us, Homo sapiens, 31% A, 31.5% T, 19.1% G, 18.4% C. This is a type of fly. This, I believe, is corn. We got some bacteria here. So take a look at it, right? What he found, though, was that the proportions of A, T, C, and G are kind of all different depending on the organism. Like there is no, it doesn't have to be exactly 25%. And so, again, he made another important observation. So I just, kind of zoomed in on a couple of these species here. But what do you notice about the amount of A, T, C, and G? Feel free to pause. So spoilers, right? Well, take a look at A and T and C and G. The amount of A is very, very close to the amount of T. The amount of C is very, very close to the amount of G. In fact, in E. coli, it's almost exactly, right? It's like 24.6, 24.3, 25.5, 25.6. So what he found is that A and T are similar in quantity and G and C are similar in quantity, which was interesting. And so because of that, we call this Chargaff's rule. The amount of A and T are equal, the amount of C and G are equal. Now, he wasn't entirely sure why this was the case. He just knew that whenever he was looking at the quantities in different organisms, that they were very close to one another. But that's called Chargaff's rule. So if we take a look here at this strand of DNA, right, do we have Chargaff's rule being obeyed or not, right? Is the amount of A and the amount of T the same? Is the amount of C and the amount of G the same? So yeah, right? If you count, for every A, there's a T. For every C, there's a G, right? Like, they're equal in amount. This, though, right? Like, again, if we take a look at this one, what do we notice here? We have some mutations. So, here's a mutation, A and T should be, bonded together, but instead we have a C here. And so, see if you can find the mutations. These would be, we haven't talked about evolution yet, but these would just be mistakes, right? Probably for the most part, like tiny little mistakes in DNA replication. But, they could be caused by all sorts of different things. Okay. Oh, and the last one. Okay. So now let's get into actually why Chargaff's rule works. So in the 1950s, Rosalind Franklin was able to capture the very first image of DNA. And so there's Rosalind Franklin. Here's the image that she collected. And then James Watson and Francis Crick kind of stole her photo. And when they looked at it, they said, okay, this is a double helix. They were able to identify that. And so in case you're wondering, a double helix is just a twisted ladder shape. So here you go. Here's a model of DNA that they made. It's a famous photo of them kind of pointing out different parts of the DNA model that they made. Double helix, though, is just a twisted ladder. So we're talking about this, right? Like it's wrapped around itself. This is the twisted ladder shape. That's a double helix. Here is that kind of simple double helix diagram that was published in the magazine, or sorry, the journal, not magazine, Nature, in April of 1953. It's probably one of the more famous journals out there, Nature, and this is one of the most famous issues. So the double helix. What is making this kind of double helix? Well, it's hydrogen bonding. Remember, we talked about hydrogen bonding a long time ago in semester 1. And that's what's kind of like invisibly holding together these nitrogenous bases. Like these nitrogenous bases are not touching one another. There are these blank spots. These blank spots are held together by hydrogen bonds that are kind of like magnets almost holding them together. And so between C's and G's and A's and T's, that's what we have is this invisible kind of like hydrogen bonding, this intermolecular force that is holding them together. And something that you might notice is that A and T's are held together by 2 hydrogen bonds. And then C and G are held together by 3 hydrogen bonds. That's why in this diagram you see 3 dotted lines between C and G, and then 2 dotted lines between A and T. And that's kind of important to know that like A and T are held together by 2 hydrogen bonds. C and G are held together by 3 hydrogen bonds. In case you're wondering what elements hold them together, it's the O and the H and the N and the H. Like these are the things that are holding them together. Again, as you can see in this diagram here. Okay. So what we call this kind of like perfect hydrogen bonding between A and T and C and G is its base pairing. So this is responsible for kind of why A and T bond together and why C and G bond together in our DNA. And it's why Chargaff's rule exists. Like without the perfect hydrogen bonding between A and T and C and G, Chargaff's rule wouldn't be followed. And again, all you need to know about that is that's kind of what makes Chargaff's rule Chargaff's rule. All right, if you have any questions, please let me know, but make sure you're filling in your notes.